Hello everybody. For today's lesson, we will be looking at chapter 5.4, Logarithmic Equations.
Here are the three objectives of today's lesson. We will first be looking at using the equivalence of the index and the logarithmic form to solve equations. Next, we will apply this property to solve logarithmic equations as well. Lastly, we will then look at solving exponential equations using logarithms. Let us first recall the concepts that we have learned from the previous lesson. We will be using these concepts frequently throughout today, so it will be helpful if you have this summary with you throughout today's lesson. Today's focus will be on logarithmic equations, and they are simply equations that involve a logarithmic expression in it. Let us first take a look at try 20 in your textbook, page 118. We will be solving each of the following equations, and we will first look at log x base 2 equals to negative 1. To solve this question, we will convert this logarithmic form into its index form by using the concept that we have learned in the previous lesson. So, we will be having x equals to 2 to the power of negative 1. 2 to the power of negative 1 is none other than 0.5, so the answer will be 0.5. Next, in part B, we have log 81 base 3 equals to x. So similarly, using the conversion to index form, we will get 81 equals to 3 to the power of x. Subsequently, 81 is equals to 3 to the power of 4, so by comparing its exponents, we will get x equals to 4. Next, we take a look at part C, where we want to solve 2 equals to log 6 minus x base x. We will first convert it into its index form and have x squared equals to 6 minus x. Subsequently, we will be getting a quadratic equation, which we will then be able to arrive at x equals to 2 or x equals to negative 3 as an answer. However, I'd like to bring to your attention that x cannot be equals to negative 3 because for a logarithm to be defined, the base a needs to be more than 0 and cannot be equals to 1, and the value y can only be more than 0. Because in part C, we see that x appears in the base as well as with 6 minus x. Hence, because x appears in the base and it needs to be more than 0, x equals to negative 3 will have to be rejected. Therefore, there is only one solution to this question, which is x equals to 2. We will now take a look at try 21 from your textbook, page 119. We would like to solve each of the following equations and then explain why one of the answers is rejected. So in part A, we have log x plus 3 base 3 equals to log x plus log x minus 1 base 3. How we will go about solving this question is that we will make use of product law to actually simplify the right hand side to achieve log x times x minus 1 base 3, where we combine x and x minus 1 together based on the law. Subsequently, we will then learn and make use of this property over here, whereby if I have two logarithms with the same base, I can say that the value of m and the value of n will be equal. So, translating it to this question, we see that we get x plus 3 equals to x times x minus 1. From here, we can simplify it and get a quadratic equation, which we will know how to solve it already, and we get x equals to negative 1 or x equals to 3. Just like what we saw in try 20, we need to be constantly reminded about the definition of a logarithm, whereby a can only be more than 0 and not equals to 1, and y must be more than 0. So going back to the question, we see that x appears here at the top, where y is typically is in this definition. So, because y must be more than 0, looking at when x is equals to negative 1, we will find that the value of log x base 3 will be undefined because the negative 1 will appear here. Hence, x equals to negative 1 is rejected. Then, we do a check for x equals to 3. We find that for every term in the logarithmic equation, they are all defined. So, the answer will then be only x equals to 3. Let's now take a look at part B, where I would like to solve log 3 minus y base y plus log 4 base y equals to 2. Before I begin, I want us to note that this answer that I'm presenting over here is not the only way of doing this. I am doing this kind of method because I would like us to practice this method over here, which we have just learned in part A. So in order to apply this method, I need to have single logarithms on both sides, and how I will be able to achieve that for this question is to apply the product law for the left hand side of the equation. And seeing in the right hand side, I have 2, which is 2 times 1, and 1 is equals to log y base y. Then I will make use of my power law to bring the 2 over here up into the power, hence I have it here. Then I will have my 2 logarithmic expressions on each side, or rather 1 logarithmic expression on each side of the equal sign. So I will then be able to equate these 2 parts from the logarithms and then get a quadratic equation. Then I can solve it and see that y is equals to -6 or y is equals to 2. But before we jump straight to saying that these are the answers, we must always find out whether our logarithms are going to be defined in what we are given. So because y appears in the base as well as in these parts over here, we find that y cannot actually be negative, so y equals to -6 will have to be rejected. Okay, so for y equals to 2, we notice that it doesn't solve any problems for us, okay, in this expression, as well as the other term for log 4 base y. So 2 is actually going to help us define the logarithms, hence y is equals to 2 will be an answer to the question. Alternatively, what we can also do is that we can combine the logarithms on the left hand side into a single logarithm using our product law, and then after that changing the logarithm form over here to an index form where we will get y squared equals to 4 times 3 minus y. Then after that, the steps that follow is exactly the same as what I have explained previously. Okay, so this is an alternative method. Moving on to try 22 in your textbook, page 120, we would like to solve this logarithmic equation. What we will first observe is that the bases of the logarithm terms are actually different, so we have to make use of our change of base law to change everything to a base of 5 first. So therefore, the second term will actually be expressed in this manner, and then we see that 25 is equals to 5 squared. Hence, we can use our power law to eventually get 2 times log 5 base 5. Then for log 5 base 5, it is equals to 1 based on the concept we have learned the previous lesson. And then after that, we will get this equation here, which we multiply by 2 across the entire equation to arrive as this. Then using the quotient law, we will arrive at this equation here. Next, we will make use of our index form to logarithm form conversion method to actually arrive at this part. Then we will be solving a quadratic equation, and we see that x is equals to 3 or x equals to -2. We will have to be rejecting the x equals to -2 due to it not fulfilling the definition of a logarithm. So the reason is because x appears in these parts, and we find, especially for the very first term, it is obvious that it cannot be defined when x equals to -2, since y must actually always be more than 0. So therefore, the answer can only be x equals to 3. We will now take a look at part B, where we would like to solve this logarithmic equation. We do notice that the bases are actually different, so most likely we will have to do a change of base. But before that, we will first bring this 6 over here down using our power law to actually arrive at this. Then after that, we will apply our change of base law to get this overall equation. When you arrive at this equation, you might probably be thinking of multiplying throughout the entire equation by log x base 3 to arrive at log x base 3 square minus 6 equals to log x base 3. Do be very careful that this is the correct way of balancing the equation. You should not be getting log x squared base 3. So they are actually different, which I have explained in the previous lesson also. So what we need to do over here is to make use of the idea that we have covered in our exponential equation solving, which is to use the substitution method because we see that we are getting something quadratic. So using the substitution method, we choose to let log x base 3 to be equals to u, such that we will be able to get a very neat quadratic equation that we can solve. Okay, so the whole idea of using this substitution method is to get something very neat for us to work with. Okay, if you are very good algebraically, you may want to skip away with this method itself. So seeing that u is equals to -2 or u equals to 3, we need to be reminded that this is not the final answer. We are trying to find out the value of x. So when u is equals to -2, we see that log x base 3 equals to -2. Converting it into our index form, we get x equals to 3 to the power of -2, which is 1/9. Then for u equals to 3, we also do the same thing and we find that x is equals to 27. Hence, we will see that x is equals to 1/9 or x equals to 27. Reminding yourself to do a check, we see that x appears here and here in the question. Okay, and because for both of these, they all need to be more than 0, which the answers actually satisfy because we're getting positive numbers as our answers. Now let us take a look at something different where we want to solve exponential equations making use of logarithms. So why is it that we need to introduce logarithms into an exponential equation? What we see in this part A is that we have 4 as the base and 9 as the base on the left hand side and the right hand side respectively. And for part B, we also see that the base numbers are actually different. So recalling what we have done in our exponential equation solving, usually we have the bases to be equal such that we can use some equating of exponents to actually solve the exponential equation. So in this case, because the bases are rather different, we cannot make it into the same base, so we need to apply logarithms. So how do we go about doing that? We will apply a common log on both sides of the equation such that we have log. Okay, if I were to be very insistent, I have brackets over here and this is what it implies. So then we can use our power law on the left side of the equation to bring down the x minus 1 to get x minus 1 times log 4. Do be very careful that I must have the brackets here. Then after that, I can divide log 4 over to the right side to get log 9 over log 4, which is equals to x minus 1. Then I have x equals to log 9 over log 4 plus 1. So when we have a common log in use, we can easily press for the value of log 9 over log 4 into our calculator easily. So if I had used maybe a log of base 2 on the left hand side of the question, I would struggle at the end because I would be seeing something like that. And this is not easy for us to press into the calculator because we still need to do a double step, okay, or rather a second step in doing changing of base to a base of 10, because our calculator is only limited to either a natural log or else a common log. So therefore, whenever we do logarithms to solve our exponential equations, we will use a common log typically. So when do we use the natural log in solving an exponential equation? We do that when we see that the base has the exponential value itself. So when we see that e is appearing in the base, we will choose to use the natural log. So why do we use the natural log in this question? Okay, it is because after I have brought down the 2x using my power law, I see that I have a ln e. And ln e is actually of the same meaning as log base e, or rather log e base e, which is actually equals to 1. So I can easily be able to write that 2x equals to ln 3 without having to divide ln e over to the right hand side. So the whole idea about using the natural log in such questions is to actually make use of this concept over here. Then after that, I will find that x eventually is 0.549, making our answer to be in 3SF. In case you're wondering whether instead of using our natural log, could we actually use the common log? Definitely we can. So our working will end up looking like that, such that after I use my power law, I will have to actually divide log e over to the right hand side. Then after that, my answer will be as such. Okay, eventually, even if you press this into your calculator, we will still get 0.549 rounded to 3SF. So using the lateral log in this question really is to help us to reduce one additional part into the working. We will now take a look at try 24 from your textbook page 121, where in part I we are given an indexes equation, and then we want to show that 3 to the power of x is equals to 36. So what we have to do is to actually combine 2 to the power of x and 3 to the power of 2x together, but the problem is that we are not having anything of the same base, neither do we have the same power. So we can't apply any of our indices laws. So what we need to first do is to recognize that 3 to the power of 2x is the same as 9 to the power of x, and with the powers actually equal already, then we can make use of our indices law to get 2 times 9 bracket to the power of x, which is 18 to the power of x. Subsequently, we see that 18 is actually 3 times x, and then we will get 3 to the power of x times 6 to the power of x. Similarly, on the right side, okay, we see that 6 to the power of x plus 2 is 6 squared times 6 to the power of x, where we will get this. Then we will be able to divide on both sides of the equation by 6 to the power of x, hence we will arrive at the answer 3 to the power of x equals to 36. Then moving on to part 2, we want to hence solve this equation for x, where we are given 3 to the power of x equals to 36, and since the bases cannot be made to be the same, so we will apply our common log on both sides of the equation, and then making use of our power law to bring down the power of x, hence we get x log 3 equals to log 36. Then we will divide the log 3 over to the right hand side and have our answer to be 3.26 in 3SF.
We will now take a look at exercise 5.4 question 11 found in your textbook page 123. We will only be looking at part A and part B. Firstly, looking at part A, we want to solve ln 2 times ln 4x equals to 3. We need to first observe that ln 2 is a value that we can compute from our calculator. Hence, what we should do is to bring ln 2 over to the right hand side. It is a very common mistake to think that we can combine ln 2 times ln 4x into a single logarithm. Take note that the product law does not apply in this case. So, following from there, we will arrive at ln 4x equals to 3 over ln 2. We can then change this logarithmic form into the index form, so we get 4x equals to e to the power of 3 ln 2. Then, pressing into a calculator for this value itself, we will get 18.9 as our final answer. Moving on to part B, we want to solve log x minus 2 equals to log 3 bracket square. Take note that in this case, log 3 is actually a value which we can press into a calculator itself. Hence, from this logarithmic equation, we will change it into its index form, and we will get x minus 2 equals to 10 to the power of log 3 bracket to the power of 2. So x will actually be the value itself plus 2. So pressing that into calculator, we will have 3.69 as our final answer. We will now take a look at question 15 from exercise 5.4, textbook page 123. We would like to be solving these two simultaneous equations. From the first one, what we will do is to make the bases all to be common first, so that we can actually equate the exponents. So for 16 and 4, we can change it to a base of 2, and then after that we will get the equation 2 to the power of p plus 2 equals to 2 to the power of 4 plus 3q. By equating the exponents, we see that p plus 2 is equals to 4 plus 3q. We then make p the subject. From the second equation, we have a logarithmic equation. So what we will first do is on the left hand side, we will apply the quotient law to get log 6 over 15q minus 3p base 2 equals to 1. Then converting it into an index form, we will have 2 to the power of 1 equals to 6 over 15q minus 3p. Or you will do some form of manipulation and arrive at 30q minus 6p equals to 6. So now that we have our third equation and fourth equation, we will apply the substitution method to solve this simultaneously, and hence we get q equals to 1.5 and p equals to 6.5.